Hello, everyone. It's nice to be back virtually in Moscow to be giving a talk to people there. Thanks, Stefan, for the invitation. So Stefan asked me to speak about some of this line of work that I did a few years back with Damien Pousse and also Amina Duman. And I'm not going to say much about the stuff that happened afterwards, but I should say that this line of work has continued by many people. So Damien Pousse has his group in Lyon, and he and Amina Duman, but also people like Denis Kupperberg and Laureline Pinault have really done some interesting things in recent years. And at the same time, there are people in the London side at UCL who I think Max might know of, who have been working on variations of Kleene algebras. And I think there are people there who are also thinking of applying cyclic proofs to that sort of thing. I was going to talk about that a little bit, but actually, as I went through my slides, I realized it was better to remain self-contained and speak about the things that I did work on. But I'm happy to sort of give pointers in those directions if anyone wants them. So also, I'm aware that many of you might not have seen much about Kleene algebra or maybe modern structural proof theory, so I'm not going to assume any of that. And so I hope you should be able to get something out of the earlier parts of the talk, and yet I hope to present actual results towards the middle and the end, so there should be something for everyone. The main thing is, I understood that it's 45 to 50 minutes excluding questions, but please do interrupt me if something's not clear, or if you have any questions in the meanwhile, which I hope can count for those question time later on.
Yeah, thank you for permission to interrupt you. I would say that what you said up to now is the best format of our seminar we appreciate. So to have some introduction in the broad field of research and then specific results obtained by the author. So thank you very much. It's exactly what we need.
Great. Thank you. Okay, I'm good. I pegged this at the right level. Okay, so let's get started. As usual with these talks, we have a title which has buzzwords. So let's unwind those words and see what we mean. And one way to, the one way I'm going to motivate this is by saying that this work is about Kleene algebra. So what is Kleene algebra? Well, I think we all have seen regular expressions, right? So regular expressions, we have a finite alphabet A, and we can create terms using the elements of A, using the constants 0 and 1, and also sequential composition, union, and Kleene star. And these can be interpreted in various ways, as we'll see. But in particular, I think the way many of us have engaged with regular expressions is in the form of rational languages or regular languages. So in particular, each regular expression E generates a rational language in the usual way. So what does that mean? That means, well, 0 is just the empty language. 1 is the language consisting of only the empty string. This is just the language containing only the letter A. Maybe here I should rather say this. This is the language E, then the language F. So that means it's the set of words that can be written sigma tau, where sigma is in the language of E, and tau is the language of F. This is going to be the language of E union the language of F. And E star is just going to be the Kleene star. So it's the set of sigma 1, sigma n, such that sigma I are in the language of E, right? I'll write this again typeset, but I'm going to assume you've seen this before. And what a Kleene algebra is it's a natural abstraction of this syntax and by its structural properties, for example, in the rational language model. So,
excuse me, is it possible to have empty string as well? When you concatenate, could it be just empty?
Yes. So the 1 here, the standard language it generates is just the language consisting only of the empty string. So if you concatenate E and 1, then it will turn. Then this language is going to be identical to the language of E.
Yeah.
Okay. That's a good question, though. Yeah, we admit the empty string here.
Yep.
Formally, by the way, that's just one interpretation. what we'll be interested in this talk is an abstraction of this interpretation. And that abstraction is a Kleene algebra. So what is a Kleene algebra? Well, we'll define it in algebraic terms. It's just a tuple like this, where, formally speaking, these symbols 0, 1, plus, times, star are the interpretations of the syntax that we have introduced above, such that, well, if you take the everything without the Kleene star, you have an idempotent semiring. And then you have these conditions here. And let's think, what are these saying? Well, this is saying that x star is a fixed point of 1 plus x star. So I'm just saying that x star is equal to 1 plus x star. So x star is a fixed point. And what do these serve to accomplish? These serve to dictate that not only is it a fixed point, but in fact, it's a least fixed point. And notice also that these axioms are not equational. So the previous, the axioms of an idempotent semiring are equational. This axiom 2 is an equation, but the 3 and 4 are actually implications between equations. They're quasi-equational. So maybe one thing I didn't say, what do I mean when I write xy less than or equal to y? Well, I just mean that xy plus y equals y. So it really is an equation. And so this concludes the definition of a Kleene algebra. So we've already seen one interpretation of regular expressions as rational languages, and these will form a model of Kleene algebra or just a Kleene algebra. But there are other models that abound. So, for example, not just the rational languages, but you can just take the algebra of languages. So this is where each letter of the alphabet is interpreted as an arbitrary language. So what does that mean? That means you have an interpretation which maps each letter to a language, to a subset of a star. And you have this interpretation of the symbol. 0 is just the empty, just like rational languages, 0 is the empty set. 1 is the language consisting only of the empty string, and the other symbols are interpreted just like the rational language model. So the key difference here is that the letters, instead of being interpreted as the singleton language consisting of the letters, they're like you would have, like an arbitrary interpretation of the syntax. Each letter may be interpreted by an arbitrary language. And that's the key difference with the rational language model. And another model, which is arguably even more interesting, is the model of relations, or binary relations. So here again, we have that each letter is interpreted by a binary relation on the alphabet. And here we have a slightly different interpretation. 0 is once again the empty relation. 1 is now the identity relation. Plus is still union. Multiplication is the composition of two binary relations, right? So that means that if we have a binary relation R and a binary relation X, then X, R, S, Y, if there exists Z, such that X, R, Z, and Z, S, Y. Right, so this is the usual relational composition. And then star is reflexive transitive closure. So just like, so if you see the binary relation as a graph, then we can see the graph having directed edges, and we can take the reflexive transitive closure of this graph, and that's exactly the relation computed by the reflexive transitive closure. And this model is quite useful because we can use this model to reason about program correctness in certain settings. And so one key feature of the Kleene algebra is, the theory of Kleene algebra is that it's somehow adequate for this particular model that's useful in formal verification. And we can make this formal by this famous theorem of that I attribute to Kozen and Krob independently in the early 90s. And this establishes the soundness and completeness of the theory of Kleene algebra for the two models, for all the models I've described so far. So unwinding this, if the theory of Kleene algebra proves an equation or an inequality, E less than or equal to F? Well, it's not hard to see that it's going to hold in one of these models, because all those axioms of an idempotent semiring and the least fixed point characterization of the Kleene star hold in these models, right? So remember, I gave you the interpretation of the symbols, and those interpretations satisfy the equations given to us in the axiomatization. One can also show that these things also imply that the equations hold for rational languages. This is not so involved. You just have to make an appropriate choice of model to get this to hold. But the key insight of Kozen and Krob, the key technical contribution, was this arrow 3. So this is the most important. We're going to see some sort of argument for this today. But that's really what the non-trivial insight is. So I should say that the results of Kozen and Krob are quite involved. It can be measured in its number of pages. So I think Krob's paper is 90 odd pages long, maybe even more than 100. I can't quite remember. Maybe Stefan remembers. And even
something like that, yeah.
And even Kozen's paper, I think, is 20 odd pages long. So and you know, that's quite elegant, that construction. It's quite elegant, simple to follow, and very, very nice. So, you know, these are involved results. These certainly celebrated results of the area. So what does this mean? It means that we have a way of reasoning about binary relations under, you know, the operations of Kleene algebra, just by a reduction to checking inclusion of languages. And this, we know, is a p-space complete problem. So by following around the triangle, we also get p-space completeness of all of these judgments. So if we want to decide, if we're trying to say reason about programs, and we formalize some property using a statement, an equation about binary relations, then we can reduce it to the analogous statement for regular languages. And we know how to decide that using, for example, automaton theoretic techniques or what have you. So this is a very, very nice result for that reason. However, it still somewhat gives us a reduction to a sort of black box technique. We still have to then just reduce it to the decision problem for regular languages. But we don't really have a good understanding of reasoning over Kleene algebra and, you know, a good notion of proof. So what we get from an axiomatization, a complete axiomatization, is we get a complete reasoning system. But we don't have anything that gives us any structural information. And in particular, we don't have maybe a way of searching for those proofs. So we have, like I say, if we're in this setting, we know that if something is a valid equation of Kleene algebra, that there will be a proof by the Gödel's completeness theorem. But we have no good way of searching for it, right? We can enumerate proofs, but that's not very efficient. So we still rely on automaton theoretic techniques to decide the inequality. But what a good proof system, like a sequent calculus style proof system or a cut-freeze system, gives us is a notion of proof certificate. And that allows us to talk about proof search. So this can serve as an alternative to automaton theoretic techniques. And this is really one of the key motifs of the area of cyclic proofs, that you get these sort of interplays between proof theory and automaton theory, where certain classes of proofs look like certain classes of automata, and you can see things in two different ways. And so that's what this research line is going to be. And we'll see in this talk that ideally a proof system should give us some optimal complexity bounds via proof search and give us some methodological results. And we'll see examples of both of those in this talk. Can I check who here is familiar? Is anyone not familiar with the sequent calculus or cut elimination?
Yeah, I think you should assume that there is some general understanding of this.
Okay, good. So I will assume general understanding of that then. That just affects the pace I'll go. So this is not a new idea to consider the structural proof theory of Kleene algebra. Many people have thought about it before for various reasons. So the starting point for all approaches that I'm aware of is to take a standard calculus for idempotent semi-rings. And this calculus can be seen as a fragment of what's called the Lambeck calculus, if you're familiar with that, or equivalently non-commutative, internuationistic, multiplicative, additive linear logic. And it just amounts to a different interpretation of the logical symbols. And this calculus is very well behaved. As we can see, so here our sequents are intuitionistic. We have only one expression on the right-hand side, and they're non-commutative. So this gamma is importantly a list of regular expressions, not a set or a multi-set. So we're in a substructural setting. We have no structural rules. We don't have exchange. We don't have weakening, and we don't have contraction. We have very nice, well-behaved rules for each of the symbols on the left and on the right of the sequent arrow. And we should interpret each sequent as you might expect. It's the product of everything on the left, taking care to do them in the correct order, is less than or equal to the expression on the right-hand side. And this system, well, maybe I should say one thing, happens to be sound and complete for idempotent semi-rings. And notably, this system is cut-free. So in fact, one way to show that this free completeness result holds is, as you might expect, we can simulate using cut the axiomatization, that's a standard structural induction, and then we can apply a cut elimination procedure. And actually the cut elimination procedure just for this calculus is rather textbook. It's quite a simple termination measure. We don't have issues with contraction, and so things go through, I think, rather easily here. So the question at this point is, how do we extend the calculus to deal with the Kleene star? And for this, there are various approaches. And the key thing here is to insist, in a proof theoretic manner, that star is a least fixed point. So Gibson proposed just taking the axioms 3 and 4 that we had before, that insisted that the star was the least fixed point, and turning them into rules in a natural way. And so these are the rules that you get from those axioms. But if you've done some structural proof theory, if you've done some cut elimination, these are not very satisfactory looking rules. So this F changes polarity here. It turns up on the left and on the right. Similarly for this F here. Here you don't have an arbitrary context, so you're not closed under context on one side. I guess you could maybe massage this to have some sort of closed under context version. But it turns out that any sort of massaging will be hopeless. So he wondered whether cut elimination holds, but Boskovsky showed that without cut, the system is not complete. So this was just an observation by taking a particular judgment that clearly will have no cut-free proof. There were other variations proposed based on this idea, but none of them are complete without cut. So since we're trying to do some structural proof theory, in particular, we're trying to do proof search, we care about having some form of cut elimination or some at least cut admissibility so that we can do bottom-up proof search. So I'm just going to reiterate, I don't know if I'm going fast or slow, so please do interrupt me if you have any questions or if something's not clear. So then an approach that's closer to the subject matter of this talk was proposed by Palka. And she proposed using an omega rule for the Kleene star in the tradition of, in the school tradition of, proof theory from the 20th century, where you decompose the E star and you just check every possible case. So this is the characterization of E star as 1 plus E plus EE plus. And based on this sort of infinite unfolding of the star, you naturally arrive at these two rules, right? You arrive at one rule, which we might call the omega rule, which checks each of the cases. And you have the right rule, which says that if any finite number of cases holds, then you can, if you can if you have a bunch of words each of which contained in the language of E, then their concatenation is contained in the reflexive transitive closure. And this is quite a nice system. It's quite intuitive, and it has an elegant proof theory. So she shows a cut elimination result, and these cut elimination results also hold for standard extensions to residuated lattices with a Kleene star known as action lattices, and this gives optimal pi01 bounds. However, this system unfortunately isn't actually sound in those systems, in those extensions for action lattices per se, but rather what's called their star continuous variants. So the cons are numerous. Because of this rule, this omega rule here, there's necessarily no notion of finite proof, right? Every proof of gamma E star delta implies F must exhaust all the infinitely many possibilities. Now, I should say that you could bound the number of cases by essentially a form of finite model property. So if you think of this from a Kleene algebra point of view, this comes down to the fact that we're complete for the model of rational languages. As a result, we know we only need to actually check finitely many iterations of the star. But that sort of restriction is very bad for methodological analysis. So if you're trying to prove things about Kleene algebra, then restricting the number of premises based on a model theoretic result doesn't give you the most robust framework. And as I already mentioned, these systems, while they work perfectly fine for Kleene algebra, when you want to take the extensions where residuals and meets, you necessarily only capture what are called the star continuous Kleene algebras based on the characterization of star I wrote down earlier, equivalently this property here. But she was able to show those variations of action algebras are contained in pi01 as a result of this cut elimination argument. So, that brings us to the current work. And the current work is inspired by sort of the recent trend of non-wellfounded and cyclic or circular proof theory in the last 25 years or so. And you can think about it as somehow orthogonal to Pauker's approach. So Pauker's approach was we take well-founded but infinitely branching proofs. And in the non-wellfounded approach, we take a completely complementary approach to infinitary proof theory, where proofs are rather finitely branching, in fact, boundedly branching, but infinitely deep, so non-wellfounded. So it's a very complementary approach to infinitary proof theory. And I should maybe, just before I get technical things, one of the main advantages of this is that you obtain you recover a good finite notion of proof, because there are certain non-wellfounded trees, namely the regular ones, that can be finitely represented by directed graphs. And it turns out in many cases that this small subset of those non-wellfounded trees suffices to get a good proof theoretic treatment of the logic in question. So let's see this in action. So we define a calculus, we do this in the natural way. We'll take LKA. This will be the calculus that just takes the calculus for idempotent semirings, and we'll add natural fixed point rules for star. So this amounts to rules for the equation 1 plus x star equals x star, right? So this was our axiom 2. And it's not hard to see that these rules somehow capture this axiom. But at the moment, we're not insisting at all that star is a least fixed point. These rules are, hold equally for any fixed point satisfying this equation here. So instead of doing what, for example, Pauker does, or what Gypsum tries to do, which is to add axioms or rules that capture the leastness of the fixed point, we're going to add a global structural condition on the proofs that will necessitate that this fixed point is the least fixed point in any correct proof. So we define the following notions. So an infinity pre-proof is just a possibly infinite derivation built from these rules. So this is a possibly infinitely deep derivation, but it will always be a binary tree. right? The derivation will always be have as its dependency graph a binary tree, but it's just possibly an infinite binary tree. And of course, when we have infinitely deep things, non-wellfounded structures, the danger is that we can prove fallacious things. And so we carve out a fragment of these pre-proofs that we call proofs. And here we're going to have a very, very simple criterion on the pre-proofs, which is that every infinite branch has infinitely many instances of the star left rule. So that's this rule here, right? I should say in most circular proof theory, there's a condition that is much more sophisticated for capturing leastness or greatestness of fixed points. It turns out for this particular setting, and crucially because we're cut free, a simple criterion like this suffices. And it turns out that these proofs are going to be sound. That's the main result of this system, of this criterion, I should say. So if we take the infinity proofs of LKA, they are sound and complete. So maybe something I'll say is these are cut free, which is a good thing, but they are infinite. Right? This is a bad thing. So let's see a proof in action. Let's actually see a first example of such a proof. So this is a proof of this judgment here. So A star B plus C all star is contained in A star C plus B all star. So what have I done? Well, I've just switched this B and C around here, right? Commutativity of union. And we can apply some rules. I won't go through this proof in detail. When we apply some rules, we eventually get to a point here, for example, where we get to a sequence that we've seen before, which is here. And here we just say, well, just repeat the process, right? That's what I'm indicating with these bullets. And if you look at the dependency graph of this proof, there's precisely one infinite branch, which is the infinite branch that loops on that back pointer between the bullets. So to check the correctness criterion, we just need to make sure that along this single infinite branch, there is a star left rule occurring infinitely often. And of course, lo and behold, there is. It's this one here. So when you're at this sequence, you apply star left to the left-hand side, you end up here, and then you decompose this, this star here. On one side, you end up with a finite derivation. So this is fine. And on this side, you repeat the process. And so you're going to repeat the star left infinitely often along this single infinite branch. So even if reading all the rules is a bit long, complex, I hope you've appreciated the condition and how this example satisfies the condition. If there are any questions, this is probably a good time to pose them. So I will say so one reason this example is interesting is because you really can't prove this unless you have a form of infinity. So this has no finite well-founded proof in LKA. This is not hard to show because the system is cut free. You can just take the proof search space and you can show that it's not closed, it's open. Also notice that this is a regular proof because the way I drew it with this back pointer means that there's only finitely many distinct subtrees. And so let's look at that definition. So a pre-proof, we can call it regular if it has only finitely many distinct subtrees. And what this means is we can write it as a directed graph. So usually the dependency graph of a proof is a directed acyclic graph. And here with cyclic proofs, we can just say we can keep the notion of a finite directed graph, but we can lose the acyclicity condition and we get a natural representation, natural finite representation of regular proofs. And the example we just saw was indeed a regular proof. And one misfortune of this system is that the regular proofs are not complete. So the previous example is not a counterexample to the completeness, but we will see an example in a moment. Right now we will see this example. So already something as simple as A star implies A star A. So if you have a string of A's and you put an A in the beginning, it's the same as having a string of A's and put an A at the end, right? So, and if you look at this proof search tree, well, in fact, this is the unique proof that can be built for this sequent in LKA. You're forced to decompose the sequential composition on the left. You're forced then to apply star left. You can never really act on this right-hand side until you've killed the star on the left-hand side. And so you can see in the proof, during proof search, that you'll have arbitrarily large sequence of this form. So you're going to have infinitely many sequences of the form A to the n, A star implies A star A. And so this will be non-regular. Now, there are ways to sort of massage the system to avoid this particular problem. So you can maybe add variations of the star rule that allows you to decompose star both on the left and on the right. And that will allow you to derive this sequent regularly without cut. But in general, there are just too many counterexamples, and you can't really get around the problem by just adding more rules. And the reason for that is because of these critical counterexamples. So I think what I'll do is I'll try give some time to these counterexamples to motivate it. So the point of these counterexamples is that it seems necessary to reason sometimes under the plus and sometimes under the sequential composition on the right-hand side. So why is this? Well, if we try to build a proof of, let's say, number 1, well, what is this saying? It's saying that any string of A's has either even length or odd length, right? So this, we know this is a valid judgment because any word must have even or odd length. But the plus rule, well, this is just like a disjunction, right? We can never actually choose which one it is because we don't know yet what length the word has. So we certainly cannot act on this plus. So we're forced to act on this A star. So we can show that the empty word is in, has either even or odd length. And that's easy. We just choose even length and we're done. And here we're left with A star implies A star plus A star. Now, what can we do here? Well, the same analysis holds. We cannot possibly act on this plus, which is the main connector of the right-hand side, because we don't yet know how long this word is. So, okay, we've extracted the first element. We know it's not empty. The left-hand side is not empty, and we've extracted this first element A, but we don't know the parity of the remainder of the word. So once again, we must act on this A star, and we're going to end up with a similar situation, except we're going to have A star implies the right-hand side, and so on. We're going to have, once again, a sequence of this form. All sequence of this form must occur. And so the key thing is that we weren't able to do a case analysis within this plus. This plus is some sort of additive disjunction, and we're not, and in our system, because we're in a sequence system, which must decompose the topmost connective, we can't really dig inside these expressions on either side of the disjunction. And this second example is similar. It shows us, it leads us to believe that we can't, we're not able to look inside, we'll look below the sequential composition, and it looks like the proof wants to decompose these expressions before decomposing the sequential composition. And so this motivates the need for some sort of deep inference strategy. So deep inference means that we don't just look at the main connective of a formula or an expression, we're allowed to look a bit deeper inside. And that's exactly what we do. Because of those examples, we realized that there's some necessity to reason under the plus and the sequential composition on the right. We still don't know if it suffices, but it looks like those things are necessary. And this motivates this definition. So this is, I guess, some form of hypersequent. You can see it as or an asymmetric form of hypersequent, and it's an expression of the following form, right? So before we had gamma e, we had a list on the left and a single expression on the right. Now we have a list on the left, just like before, but X is a multi-set of lists, so it's become a lot more complex. And what's the idea here? The idea is we interpret this multi-set as a big sum of a product. So why did we choose that? We chose that because we realized that we need to reason underneath plus and times on the right. So we added some structure to the meta level, so meta connectives, the commas, that allow us to see the formulas underneath sums and products. So far, this is, this may work, this may not work, we're not sure. But this gives us a quite well-behaved system. So I'm not going to go through all of these rules, but let me highlight a few. The left logical rules are exactly the same as LKA. But now we have right logical rules that are somehow the analogs of the left rules. So before, the right rules were non-invertible. You had to make choices going up, but now the right rules become invertible. And that's very good for proof search. And you can think of them as just implementing the same logical behavior as the left rules, but the more refined structure on the right-hand side allows us to actually realize them as bona fide rules now. And now a lot of the other rules we would like just become structural rules. So we have, because we have sums on the right, we can weaken new sequence because this is disjunction. So we can always weaken new lists. And we can also contract them because, again, the sum satisfies contraction, whereas product doesn't. And finally, we have this little rule here, which is quite important, which is the K rule. And this says that if you can derive that the language gamma is included in the language X, then you can stick the expression E in front of both languages and they're still contain each other. So it's some form of functoriality, or if you've done some modal logic, it looks a bit like the K rule of modal logic. And one thing that's important is that all of these rules, the logical rules, are invertible. And this rule, it's not invertible, but it's actually weakly invertible when E is atomic. What does that mean? It means that if the bottommost expression is valid when E is atomic, then so is the upper expression. But it's not the case that truth is necessarily preserved. The logical rules preserve truth, preserve and reflect truth, whereas this K rule reflects validity, as well as preserving validity. So from here, we can actually define, I have a chat here. So Stanislav asks, can you have a proof system for this particular sequence as a two-player game where the first player generates a sequence of A's and the second player covers it by either an odd or even number of A's by using some strategy? I think one can see the proof I'm about to give as inducing some sort of strategy, but I don't think it will be a strategy that covers, right, yeah, so the covering will be induced by, I guess, some sort of derivative argument. So you could take what's it called? When you keep taking derivatives of an automaton, of a regular language, and you get the Myhill-Nerode theorem, right? You can keep taking the derivatives and you're guaranteed, no matter what the first player does, to be covered by one of your iterated derivatives. And the Myhill-Nerode theorem tells you that there's only finitely many of those. So you can see it in a game theoretic sense in that way. And actually, indeed, that's what we'll do for the completeness proof here. So the main aim here is to show that not only were these considerations of using plus and times necessary, they'll actually suffice to give us a regular cut-free system. And so for this, we need to define a strategy. And so for this, we'll, instead of defining the strategy explicitly, we're just going to define a normal form of proof. So we call a pre-proof leftmost if the principal formula of every logical step is at the beginning of the list, either on the left-hand side or the right-hand side. So what does that mean? That just means on the left rules that the gamma is empty always. And on the right logical rules, it means that this delta is empty always. So that's what leftmost means. And that's going to be interesting. Why is that an interesting notion? Because we have this invariant. Only finitely many lists occur in a leftmost pre-proof. Why is that? Well, it comes down to just establishing a particular ordering on the suboccurrence relation. You can see that every list in a leftmost pre-proof is going to be monotone with respect to the suboccurrence relation or the subformula relation. And this means you'll only have lists of polynomial length. And notice also that as a result, leftmost infinity proof can be transformed to a regular one of the same conclusion. So since only finitely many sequents occur, we can cleverly place back pointers at the appropriate places. What we must do here is we must wait to make sure that we've crossed a star left rule to make sure that we don't break the proof. So it could become only a pre-proof, but given that it's a proof, every infinite branch crosses infinitely many star left steps. And so we can just take this proof, and eventually, since there's only finitely many, we can loop back and we just make sure that there's a star left in the middle. Now, another thing I'll say is that for arbitrary cyclic proof systems, the argument is not so simple to get this regularity from, to go from this property to this property. Here it's quite simple because of our simple correctness criterion, but for arbitrary systems, it's much more complex. More generally, the correctness criterion will be some omega regular condition on the infinite branches, not just a fairness condition. And from there, the fact that you can go to a regular proof is actually a corollary of Rabin's basis theorem. Because it's an omega regular condition, the class of proofs of a theorem is in fact an omega regular tree language. And so since we know there's proof, we know there's going to be a regular one by Rabin's basis theorem. So that's more involved, but here we have a much simpler direct argument. And the idea here is, like I said, you can limit the succedent size using the structural rules as you might usually do in a proof search argument. And you can place back pointers once star left rules have been crossed. Since there are only finitely many lists occurring, by the pigeonhole principle along each branch, you must get a repetition at some point. And from here, we can establish our completeness result. And this is from a paper of mine and Damien Pousse from 2017. The leftmost infinity proofs are for HK are complete. And from here, and the idea here is we just implement a proof search strategy. So by invertibility, we can always apply logical rules without losing any information. And then when we get to a normal form, we know that the leftmost expression on each side on all the lists is atomic because we've applied all logical rules. And then we can apply the K rule because of the weak invertibility of the K rule. And one thing that's crucial here is this lemma here that allows us to, in some cases, apply weakening on the right, which is crucial because we need to control the size of the right-hand side. I don't go into the details here because they're a bit, they're not so technical, they're just a little involved. And also I'm conscious of the time. But of course, note that as a direct corollary of this theorem, we also get that the regular proofs are complete. And so let's just, oh, that's the next corollary indeed, just because of what we said on the previous slide. So we can see, instead of giving you the details, I'm just going to show you some examples. So this is the proof, this is the example we saw earlier that could not have a regular cut-free proof in LKA. But in HKA, we do have a regular cut-free proof. Why is that? Because we can do a case analysis on the right. So the first thing we can do is we can kill this plus and we get a comma. And then we can also decompose this inside because we can see it. So this gives us this comma. And now we can start decomposing the left-hand side. So if we're empty, we get this finite derivation, which has even length, and so we're fine. Now, if we're non-empty, then we know we're non-empty. But since I know I'm non-empty, I know that if I'm in the even case, then I'm non-empty, so I can take out one of the letters, and same with the odd case. So in the even case, I take out a pair of A's, and in the odd case, I also take out, I don't need to take out anything yet, because I already have the A in the odd case. And now I get into this form where every list starts with an A, and I can apply the K rule to kill the A's, and I get to this situation. But now I've seen this sequence before, right? I can just loop back to here. Now, one thing you should notice here is actually that even though it's the same sequence, you have that these two have flipped around, right? Because if it's even before and you take a letter off, it becomes odd. And if it was odd and you take a letter off, it's even. But you're still even odd. So the same case analysis applies, but actually the two sort of flipped around. So that's quite an interesting feature that can happen in these cyclic proofs. And I think maybe to Stanislav's question, you can think of these finitely many lists that can occur in the leftmost proofs as maybe the sort of covering that you're after. So the right-hand side is the opponent, and he covers it by looking at all the derivatives of the right-hand side, I guess. And this is an example for the other sequence that I didn't go into, so I'll skip this. So I'll state some further results. So one thing I mentioned before, again, is that we have a very simple correctness criterion. It's just the fairness of the star left rule along infinite branches. And this means that checking whether a directed graph, that's a labeled directed graph, is a pre-proof, is a proof, is actually a polynomial time property. Why is that? Because we can just take its dependency graph and we can delete the star left rules and we can just check it for acyclicity. If it's not acyclic, i.e. if it's cyclic, that means there's an infinite branch that is not fair for star left. And the converse holds too. And of course, this is an NL complete problem. And so yes, this is an NL complete problem. And so we're in particular in polynomial time. And actually, because it's easy to check, and because we have a good proof strategy, we actually get an optimal proof search procedure. So the proof search procedure I described using leftmost proofs actually exhibits a p-space bound. And so this gives us a lot of nice results that we wanted. We wanted a good proof system that we could check efficiently. We wanted a notion of proof search, and we wanted to prove some methodological results, which I haven't gone into yet. But the nice thing about this proof search procedure is if you've done some proof search arguments, then it's basically a loop check-in procedure. Except that we don't need to backtrack when we've hit a loop, because this is a cyclic proof system. So we can just end the proof search when we hit a loop.
Anupam, we are at 20 seconds slide out of 35. How much time do you expect to?
I was about to ask, because this is the end of this section. So we started 5-10 minutes late. How much time do I have left? Because I could end here if I need to, and we can just call it a day, or just present conclusions, or I could present one of the two remaining sections. The two remaining sections are further results, so I don't mind skipping them.
Yeah, of course, yes. Generally, as we said, we are flexible enough, but you spent your about 50 minutes, so now just decide. Okay, go on.
Okay, so so it sounds like I should conclude, which I'm happy to do. So what I will do is I will go to the conclusion slide. And I won't present the previous things, but I can make the slides available for you. So the main thing I wanted to show was this recovering completeness, which is actually that we can right, so I won't show this. I'll stick to what I said.
Look, it's okay. Just you should just try to kind of squeeze, but yeah, don't try to do it too hard. So just go on and tell us whatever you want.
Maybe if I could have something like 7 minutes. So I think I would like to show this one thing.
Oh, perfect. No problem. All right. Yeah.
Also, since I started a bit late, I think. Oh, but I've definitely had 50 minutes. All right. No, you're right. You're right. Okay. No, let me conclude. This is the right thing to do. Okay, so so one thing I didn't have time to present, but that is a further result. So I said we wanted two things at the beginning. We wanted a good notion of proof search, which I've showed you. But we also want to get some methodological results. And one such methodological result is completeness, which I showed you right at the beginning. And in fact, the system that I presented to you enables just that. So I won't show the argument, but I can let the slides be available. So soundness is direct, and I said that Kozen and Krob have these famous completeness results, but we can actually go and establish completeness in a different way. By soundness, we hold for the rational language model. We've already shown completeness for the system of regular HKA. And actually, in a later work, me, Damien Pousse, and Amina Douman, we showed that from here, you can translate back to here purely proof theoretically. So this argument just manipulates proofs, and using a series of proof manipulations, we're able to actually construct a proof in this theory of Kleene algebra. And this gives us an alternative demonstration of Kozen and Krob's results. And actually, we're able to do even more. We actually hold for the left-handed case. Now, I haven't had time to say what that is, but it turns out that actually this axiomatization is in some sense redundant. You can also take a substructure of Kleene algebras called left-handed Kleene algebras that rejects this axiom 3 I had in that first slide. So you only have one of the least fixed point axioms, but that actually suffices to be complete for the rational languages, the theory of the rational languages. That's a result of Boffa in 95. Well, actually, he showed how to reduce Kozen's result to one of left-handed completeness. This has been given other treatments co-algebraically by Kozen and Silva in 2012, but all these proofs are rather complex. And one thing I believe to be the case is that our argument seems to be more direct and simpler. And both these arguments, and our argument, both for the left-handed case and actually much simpler for the non-left-handed case, expose once again this very, very nice interplay between proof theory and automaton theory that I won't go into. So the motto of this is again that proof theory can give us methodological results here. And I also said what I didn't have time to do is we actually have works on this on extensions of Kleene algebra, but with residuals and meets. And actually, this is an area that Stefan has worked on considerably. So I think in a first iteration of this talk I gave a couple of years ago, because it was still open, I had the word action here. And this has since been resolved by Stefan, who showed that, that the theory of action lattices is a sigma 01 complete. But there's still some open questions here. As far as I know, still open questions, Stefan, in this area. But I know Stefan is on a mission to exhaust more results here. So I will end my talk there. Thank you very much for your time.
Thank you for saving some of our time. And we have time for questions. It was very kind of intensive, and really it was a good survey as well as your own results. So what are the questions?
Well, I think I have a small, more of a comment. Well, it was a bit of a pity that this way from circular proofs to, or regular proofs to Kleene algebra proofs were omitted. This result with Amina and Damien. So, yep, this is just a comment. And the question was for Kleene lattices. So, do you think about distributive or non-distributive case? This should be
just the non-distributive, just the Kleene lattices.
Yeah, but maybe in this how to call it, deep inference format, the distributive case could be easier. No?
That's a good point. I didn't think of that. Is that
because
a distributive case?
Yeah, because here you extensively use the distributivity between plus and multiplication.
Yeah. Yes.
And
Yeah. Absolutely.
there, maybe this could help. So, well, just bold guess. I tried to think something about Kleene lattice. I didn't. Well, all I managed to do, you've seen at this meeting in Göteborg. So, but maybe distributivity could help here.
I didn't think of that. So it's still open for the distributive case, you said?
I don't know. There are some results, I think, by Nakamura from LIX 2017, maybe.
Is that where he shows the X-based completeness of the relational model of Kleene lattices?
Yes, I think yes. So the problem here is that here you have a very good model, the standard model of regular expressions. There, all this fails. So therefore, you will have.
But he does. He nonetheless establishes a good notion of automaton. This is how he gets it. Yeah. Regarding the HK stuff, actually, Stefan, I prepared. I can send you the slides because there's a self-contained proof of the non-left-handed case in here, which I think is much easier than our left-handed proof. We actually had both at the time, but we only wrote up the left-handed one because it was more interesting. But I can share those with you, or we can talk about them privately at some point.
Yes, but anyway, it would be really nice, and at the same time, usually if you just leave your slides, we put it on the seminar page. Yeah. Have you finished your question, Stefan?
Yeah, the question is finished. Yeah, so this is all the extra stuff. I think we'll discuss it privately because it's all this untangling of these circles, and this is technical.
There was also a question of Stanislav Kikot. Perhaps he can ask a question just orally. Stanislav.
Yes, but you can probably read it. Can you? At the
beginning, okay, they can read
it.
Can you say a few words about your co-authors' recent research on this topic? Because it's not clear about what topic and what co-authors. Perhaps you'll explain.
But you mentioned something at the beginning of your talk.
Yeah, I think. I mean, there's been a number of these, number of results since then. Now, there's a lot of research on Kleene algebra and extensions. So, namely, extensions to lattices or residuated lattices or residuated algebras, and also extensions by concurrency, so concurrent Kleene algebras. Now, not so much of this has been on the proof theory side, but I would single out maybe a paper by Amina Duman and Damien Pousse on an axiomatization of Kleene lattices, the relational model of Kleene lattices. So they give this nice work where they give a complete axiomatization of identity-free Kleene lattices in the relational model. So I think the title says just Kleene lattices, but it's for the relational model. And this is a nice result. And my understanding is that even though that paper doesn't have any cyclic proof theory in it, I think in the background they were using some cyclic proof theory for the ideas there. I wasn't involved with that. I already mentioned this work of me, Damien, and Amina, where we gave an alternative argument for the left-handed completeness, which is quite nice. And then since then, so Damien and also Denis Kuperberg, along with their PhD student Laureline Pinault, they started getting interested in seeing Kleene algebra and variance as type systems. So there was this work of myself and Damien Pousse from 2018, a different work from the one cited here. Again, you can see some of this stuff on the slides, where we give a form of cut elimination for non-well-founded proofs, in particular to give a treatment of action lattices, so extensions of Kleene algebra by division and by intersection, by meets. And this relied on a computational interpretation of the proofs of action lattices. And then from here, I know that Damien was thinking that this should be treated as a first-class citizen, and what can we do with this as a programming language? And they recover a sort of form of Gödel system T by taking Kleene algebra with structural rules and taking the computational interpretation as the subject matter. I also have a work, but not so much motivated by the Kleene algebra side of things. So there's a recent preprint of mine that's available, on Gödel system T in a cyclic presentation. Yeah, I think those are the most relevant works that I could mention.
Thank you.
Thank you. Thank you. I have one more question. So does this research have anything in common with cut-free proof systems of Ley and of Shari from your calculus?
Good question. So the result you mentioned, so just for everyone else, so this is a result where they give a very, very well-behaved circular proof system for the mu calculus. And they use it, again, proof theoretic techniques to recover a self-contained completeness result of a standard axiomatization, so-called Kozen's axiomatization of the mu calculus, reproving a result of Walukiewicz in the 90s. In some sense, thematically, it's very similar. So they're trying to do the same thing. They're trying to use structural proof theoretic techniques to get alternative proofs of results that we don't fully understand yet. I will happily say that their result is certainly more involved and more, I think, significant than the one here. Their tools are much more complex. However, the one thing I'll mention is that the discipline of cyclic proof theory that they take is slightly different from here. But actually, it's sort of a normal form of the cyclic proof theory that we consider. So like I said, during the talk, the general notion of a cyclic proof is you have some sort of fixed point, and then you have some sort of omega regular condition on the infinite branches, the so-called progress condition. Now here we started by imposing that, but actually we didn't need that. The fairness condition was enough in this setting. Now what Bahare Afshari and Graham Ley do is their starting point are these annotated or labeled, I think they're called annotated tableaus or tableau with names, sorry, of Stirling and Juncker-Appenich. And this system is very, very clever because it was inspired by the cyclic proof systems of Walukiewicz and Nowinski. So this all sort of started in 95, where the systems of Walukiewicz and Nowinski, they presented a circular, well, they call it a tableau system, but it's actually just a circular proof system with an omega regular condition on the branches. And on analyzing that, they realized that by taking the product of a proof and a deterministic parity automaton recognizing correct branches, they were able to just annotate each sequent with the state of the deterministic automaton, essentially, but they just simplified this annotation. And this gives you an almost deterministic way to talk about cyclic proof theory. So before, checking an omega regular condition on all infinite branches is a sort of non-deterministic thing. And so it's hard sometimes to construct proofs or manipulate proofs. And they came up with a normal form that where it was much easier. And then what Bahare and Graham did was they actually refined that normal form even further and gave it a bona fide proof theoretic presentation in the sequent calculus. And then through a series of quite elegant proof transformations, they showed this completeness result. Maybe I've digressed a little bit. So the thing I would say is it's thematically very, very similar. I think we're trying to do the same things. We have the same sort of goals. We want to use proof theory to talk about we want to apply structural proof theory to other areas. And I think in the background, there's all this sort of relationship between proof theory and automaton theory that certainly motivates me. But like I say, the actual tools in play are a little bit different.
Okay, thank you. Any more questions?
I would like to comment maybe on Stanislav's last question, that if about the K rule. So if you try to go to a broader setting of PDL, then your letters in these, say, ABC you have here, they will become modalities, and this will be indeed the K rule. So I think this is a motivation just for the name.
Okay. Anybody else would like to say anything? Yeah, I think it was really very interesting field of research, also presented by Stepan in our community, but it was very nice to have new results from the outside. And thank you for coming, and thank you for Stepan for the invitation. So let's applaud to the speaker.
Thank you. I just see that Stanislav asked.
Yes, does there exist maybe some lecture notes on cyclic proofs?
Yeah, but I think
it's presented in a systematic way or a textbook or something.
I'm afraid not. And I think one of the reasons is because you have quite a few different communities that really see it in a different way. So you have the modal logic community, which started in Novinsky and Velikiewicz, and that sort of spawned parallel research in the proof theory community. So proof theory, then you had the French school. So people like Luigi Santapanali and then David Bell, Alexis Sorin now drives that sort of school. Also now the Lyon group, Damien Pousse, Amina Duman, people like this. And they're really motivated in seeing circular type systems, essentially. So fragments of linear logic with fixed points, and trying to see proofs as typing derivations. But then you also had the London school, where they took predicate logic with a form of inductive definition and applied the same techniques of the modal logic setting. But these all sort of went in different directions. And so there's no sort of, there's not even standard vocabulary, actually. There's a little bit of standard vocabulary, the notion of maybe they all share a single condition. And that's not to mention, of course, the Russian school. I mean, you have people like Daniel Shamkanov and his collaborations with Yuri Savatiev on variations of provability logic. And I would say it's still not quite there, it's still not quite ready for a textbook, because most of these people are using cyclic proofs as a tool, not a subject matter. And so it's not necessarily the case that we can all communicate. So we had this, I mean, Stefan was here for this meeting that we had in Gothenburg. And I think people who are working on the, on the modal mu calculus side, like Ida Venema and Sterling, I mean, I think these people are really, they would say themselves that they're not proof theorists, right? So I think they are doing a different thing to us. At the same time, they have access to tools that I think we should be taking advantage of more. Like your reference to Bahari and Graham's work, I think is something that I think our community needs to take advantage of more, because it gives us a very well-behaved normal form of circular proof.
Okay, so I think we really are cycling. We finish the seminar and then going to cycle again and again. And also we have different cycles in different communities. So it's very good that our cycles are interfere sometimes, as we have today. So again, thank you very much. It was really a very interesting talk and good discussion after this, which is more important parts of the seminars. And so we say goodbye to the next meeting, perhaps early in summer or of course in autumn. So thank you very much again. We are closing.